So today we're going to be going over just a power electronics problem over power computations. And in this problem, we are given a sinusoidal voltage source with one harmonic, a um, 240 square root 2 sine 2 pi 60t, and it's applied to a nonlinear load. So it's going to result in a current that is produces harmonics. Now we have the fundamental frequency here as 2 pi 60, and we are ending up with this harmonic there. Now it says determine the power absorbed by the load. Okay, so power absorbed, what do we know? Well, instantaneous power is equal to what? V times t, or V of t times I of t. Now this is if you have, this is only true for harmonics that are the same. If you have noticed so far, whenever you're trying to multiply voltage and current, they have to have the same fundamental frequency, or the harmonics must be the same. Otherwise, they don't add up very well. In this case, we are trying to find the power absorbed by the load. Now, there is an equation we can use in this case, and these equation works for nonlinear loads, linear loads, or nonlinear sources, or nonlinear loads. No matter what you do, this will work. What you will do is you'll take the DC components, you will multiply them together, and then you will add the summation from n is equal to 1 to infinity of Vn times In over 2 times the power factor, or your cosine of the angle between them. Now, just to clarify, this is the voltage phase shift, or phase, and this here is the current phase shift. Another way you can write this equation is this Vn over 2 can be rewritten as not VRMS, but Vn RMS times In RMS. So if you are in the exam or any type of problem are given RMS values for the sources and the load current, you can then say, you can use this equation. N represents the number, the harmonic number you're going for. So the fundamental frequency will be the first harmonic. Then, depending on if you go by like if n is equal to 2x plus 1, where x is an integer, it goes by even numbers. Actually, this would just be 2x. Then you have, your first harmonic, then you have your second harmonic, third harmonic, and sometimes you might end up going from second harmonic to fourth harmonic to sixth harmonic, where n is equal to this, or in three-phase rectifiers, which we'll go over later, you have 6, 12, 18, and so on. In this case, we're only given 2 and 4. So you could call this 1 and 2, 2 and 4, however you want, it doesn't matter. But in this case, we use this equation to solve for the power absorbed by the load. So the power absorbed by the load is going to be equal to, well, we don't really have a DC value, so we can say 0 times 0. That does not mean the power absorbed by the load is 0, because you have to add the AC terms. Now, Vn times In. Let's look at the first harmonic, which is going to be our first AC term. Vn times In. These are only the magnitudes. Okay, be very important. It's very important you remember this. These are only the magnitudes. So we have 240 square root 2 times the current I. Now you have to make sure the harmonics match. You have to make sure what's in here in your problem matches. If they do not match, you cannot multiply them. You cannot do this. You cannot multiply this harmonic with this harmonic, because they don't match. They will not add together, or not multiply together. So the magnitude for the harmonic that we're looking for is this harmonic, so this is 8 divided by 2. You cannot forget this divided by 2. Then also don't forget cosine of the angle between them. In this case, the phase angle for the first harmonic of the voltage is 0 minus the phase shift of the current, the first harmonic, which is 0. Then you add. Remember, we're doing a summation from 1 to infinity of however many harmonics are given. Then we add, okay, are there any more harmonics in the voltage source? No, so we have 0 times the magnitude of the second harmonic in the current source, or the current. Well, that's 4, but do we really have to do the rest of this? No. We can say blah, 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 whatever that is, but we know 0 times 4 is always going to be 0, no matter what the power factor is. I say power factor because this is our power factor for this harmonic. Later on, we will, of course, find out the power factor of the load. But now we notice what that's 0, this is 0, so the only term left is this. Cosine of 0 minus 0 is 1. Go ahead and plug it into your calculator. And what we're going to get is the power absorbed by the load is going to be equal to about 1,570, or 1357.65 watts, or 1.358 kilowatts. So there we go. We've solved the power absorbed by the load. Now the next part of the problem, we're looking for the power factor of the load. If they say find the power factor, it is most typically going to be at the load, if not specified. So just to keep that in the back of your mind, in the exam, if they ask for power factor, it's going to be at the load, because that's usually what they're asking for. So power factor, the load power factor. Now there's another equation, a nice equation we can use. The original, or part A answer, power absorbed by the load, divided by V RMS times I RMS. And again, these are the magnitudes. Okay, so what are we going to do here? Well, do we know VRMS? Do we know IRMS? Well, let's look up here. We don't know exactly what those values are, but we can definitely find them through this relationship of amplitude and RMS. We know V RMS is going to be equal to Vm, the amplitude of your signal, divided by square root of 2. Same thing for current. Now this is only for this would only be for like one term. Sorry, this is supposed to be square root of 2. This is only for one term. What if you have multiple terms, just like our current? If you have multiple terms or harmonics in one current, you must take the so-called superposition, or the square root of the squared sum. So those are kind of big words, but all we're going to say is VRMS, this is easy, is equal to Vm, which up here it gives us as 240 times square root of 2, divided by square root of 2, and that's going to be equal to 240 volts. And just so we know this is RMS, we'll put 240 VRMS. Now, IRMS, we're going to have to use another equation here, but this one should come off the tongue pretty well. We're going to take the square root of the addition, or the sum of all of the terms squared. And remember, this is RMS. For the DC term, we'll take I naught and we'll turn it into an RMS value, really. Okay, and then take the sum of n is equal to 1 to infinity of the RMS terms again. I want to make sure I get this right here. So I squared in RMS. I'm pretty sure it's going to be I0 RMS. I don't know why I have here just I not squared. That's a little weird, right? So anyways, we won't have to worry about that DC term. I'll make sure and clear that up by the end of the video. But for right now, we know this value is going to be 0 because we have no DC term. So now what we're left with is just the summation of the squared RMS values. So let's look at the first harmonic when n is equal to 1 for current. Well, when n is equal to 1, or the first harmonic we're looking at, is this term. Im, the amplitude of the current for the first harmonic, is 8. So what we're going to do is we're going to say 8 over the square root of 2 because it needs to be an RMS. And we square it. Then we add, because we're doing a summation, to the second harmonic. What's the second harmonic amplitude? Well, that's going to be 4. We're looking at the second harmonic. So this is 4 over square root of 2 squared. And now we have to, take that value, and I get about 6.325. And this is going to be in amps RMS. Okay, but we're not done yet. We found VRMS, we found ARMS. But now we have to come back here and plug it into the equation. So now we have 1357.65 divided by 240 times 6.325. And I'm going to put arrows here so we know exactly where these came from. And now what we're going to get is this. We get about 0.894. This is power factor. All right, so now part C. We're looking for the total harmonic distortion, the THD, of the load current. So for part C, we're looking for THD. All right, so let's figure out what is the equation for the total harmonic distortion. Well, there are two you can use. One might be easier than the other. The one I'm going to use is this. I'm going to use the square root of the square RMS, the total square RMS, by the way, minus the first harmonic, the first RMS harmonic squared, divided by, again, the first harmonic squared, the first RMS harmonic squared. And remember, this is for current. So we know these values. I squared RMS, well, we know IRMS is 6.325. Do we know the first harmonic squared? Well, that here is this one. This is the first harmonic, and this is the second harmonic. Okay, so then what we do is we do the same thing that we did above, 8 divided by square root of 2 and square it. Do not forget the square, you will get the answer wrong every single time. And you cannot forget the square root, or, the square root anywhere. There are a ton of square roots in here. What I'm going to get here is about 0.5. And total harmonic distortion is usually in percentage. So we're going to multiply this by 100%. And we'll get a 50% total harmonic distortion. Now, part D. We're here to find the distortion factor of the load current. So distortion factor and total harmonic distortion are related. Well, they're related by this equation, the square root of 1 over 1 plus THD, or total harmonic distortion, squared. It's also equal to this other one. In some cases, they're going to ask to solve for distortion factor first. If they do, this is the equation you use. I1 RMS, so again, the first harmonic of the RMS current, divided by the RMS current. So what we're going to do in this question is I'm going to solve for both to make sure they're equal. And this is something you can do during the exam if you are unsure about what you're going to get. Now, total harmonic distortion is 0.5. So I'm going to square that, and we're going to get a value that is, let me check, it's going to be about 0.894. Now for this one is going to be I1 RMS, which is 8 over square root of 2. This one does not have to be squared, divided by IRMS, which is 6.325. And now what we're going to get is, let's see what we get here, about the same value, 0.894. So good thing we checked here, they're the same. So distortion factor is this value. Usually, if you're unsure about whether it should be percentages or not, factors are usually coefficients, and then total harmonic distortion, just put it as a percentage. You can probably leave it like this and he'll take the answer because it is the answer. But I'm seeing most of the time as solutions, they say percentage. But that's going to be it. That is how you solve a power computations problem with Fourier transforms and multiple harmonics. If there were more harmonics, you do the exact same process, except your IRMS here would end up having more terms, and this would also have more terms. So the process is the exact same, using the exact same equations, just making sure you're adding on those extra harmonic terms. And one thing to take away from this is you cannot multiply harmonics that are different. If you're multiplying harmonics that are different, you're doing this wrong. You have to stay in the same harmonics. All right, but hopefully this was helpful. If you have any questions, please comment them or let me know. If I did something wrong, please let me know, but I don't think I did. But hopefully y'all can learn from this. Thank you.